this in computer science. And on the practice side, it's certainly the case that if you look on the internet, you would get the impression that monads are the most exciting thing in computer science. So this is a very, very small extract of the list of monad tutorials that you can find on the web. People say people compare monads to all kinds of very peculiar things. I particularly like the class of hard drugs. But actually, that one is probably the best. This year, you can actually buy this one if you feel the urge. But they're also kind of big business. So here are three of my colleagues in Microsoft, all of whom are making much from monads. So this is Simon Peyton-Jones, who I guess many of you have heard speak on the subject before. So he ships the GHC compiler for Haskell, whose logo up here indeed is basically a lambda and this monadic vine that I'll be talking about a bit later. Over here is Eric Meyer, who used to be a functional programmer and has then gone off and been in charge of things to do with SQL, C#, VB, and this kind of thing, Microsoft in Redmond. And he's responsible for the language integrated query facility, which is in VB and C#, which is based very much on monadic ideas. And then down here is Don Syme, who's in my group and is responsible, like Simon is in my group, and is responsible for the F# compiler, which has this computation expressions and asynchronous workflows features, which are an attempt to bring these monadic ideas into the F# language that Microsoft ships. But this stuff is all in the world of slightly woolly, waffly, shipping real programming languages with lots of warts. So I'm going to start by taking us back to the basics and thinking about the semantics of programming languages, because that's where things actually are true, rather than being almost true like they are in most of these settings. So I'm going to start very gently with programming language semantics, because I'm given to understand that certainly denotational semantics is not taught as widely as once it was on this side of the Atlantic. I had a referee report a few years ago which said, denotational semantics, didn't that fail in the 1980s? Which was a bit galling. But anyway, so basically, just to refresh your memory from your undergraduate career, so operational semantics kind of looks like this. So here's something for some imperative language. We say a big step semantics, a command and a state, tuple together form a configuration, and they may do a big step evaluation to give you a new state. Or we can have a small step transition system in which a configuration of command and state takes a little step to a new command and a new state. And for a lambda calculus-based language, we might have a small step transition relation like this, where the application of a function lambda x.m applied to v steps to m with v substituted for x. So these kind of things are very easy to define, but then they're kind of quite hard to work with. Denotational semantics, we put a bit more work in up front to understand our language, and then perhaps we can have some nicer proofs about programs later. So denotational semantics is a compositional interpretation of phrases of the programming languages in terms of some more abstract mathematical objects. So what kind of objects we pick to interpret phrases in a language are obviously going to depend on quite a lot of things. So they're going to depend on the type of the phrase, so different sorts of thing, different types of thing in your programming language will be different mathematical objects. They will depend on properties of the language as a whole. So whether it's sound to interpret a particular small piece of syntax as a particular kind of mathematical object will depend upon the things you can do to that small piece of program in the rest of the language. And finally, what kind of objects we choose as our denotations will depend on what aspects of the behavior of the program we choose to observe. So for the same language, we could have lots of different denotational semantics, some of which just track the input-output behavior, some of which would track complexity, some of which would track other properties. So we've got a lot of choice in how we set up denotational semantics. And it's quite difficult to find good sets of objects to interpret programming languages well. So the first thing is, because we're trying to be compositional, the meaning of a small piece of a program the meaning of a large program has to be built up compositionally from the meanings of all the little pieces. And that means that the meaning of a small piece of a program has to somehow encapsulate within it all the observations that you can ever get by sticking that small piece into a larger program. So you have to have quite a lot of information there. You have to be parametric in the context in which you're going to be placed. But you don't want to put too much content in there, because part of the aim is that we want to identify programs which have the same observable behavior. We want to abstract away from inessential detail. So if we put too much detail into our denotations, then we will distinguish too many things. So we have to make sure that we identify things. So if you find a good collection of values to interpret bits of your programming language, you've already done a whole lot of meta theory about your programming language, kind of before you even look at the denotations of any individual programs. So here's the obvious starting example. This is everybody's favorite toy programming language. It's the while programs, going all the way back to the beginnings of our subject. So as I guess everybody knows, commands are skip, assignment of the value of an expression to an integer variable, sequential composition of commands, some kind of conditional, and a while loop. And we can give this a denotational semantics using sets and partial functions. So if we define the set of stores to be mappings from our global variables to the integers, then we'll interpret our expressions as functions from stores to integers. So the meaning of an expression, you give me the store and I'll tell you the integer to which it evaluates. And the meaning of a command will be a partial function from stores to stores. And it's a partial function because you've got the possibility of non-termination introduced by having while loops in the programming language. So here's what the denotational semantics looks like. So the denotational semantics of some expression or term is given inside these funny brackets, semantic brackets. So the meaning of x gets e, so inside here is a piece of syntax, is going to be, this is a command, so it's going to be a function from partial function from stores to stores. If you give it the store s, it gives you back the store s, where x is updated with whatever the meaning of the expression e is in the store that you first started with. So it's implicit in here is that expressions don't have any effect on the store themselves. And the sequential of composition of commands is modeled by the sequential composition of partial functions. The meaning of a conditional expression, if you have a conditional expression in state S, then it will give you back the state you get by running C0 in state S if the expression that you're looking at evaluates to something non-zero, and it will give you back the whatever C1 gives you for state S if the meaning of the expression is 0. And the meaning of a while loop is given by this least upper bound of a chain of approximations. So the collection of all partial functions from states to states has a natural order on it, the extension order on partial functions. And we can construct the least fixed point of this operator. So this takes a partial function on stores to a new partial function on stores. And we'll find its least fixed point by iterating up from the completely undefined partial function, which as a set of pairs is just the empty set. And so the way this works is says you give me an approximation, you give me f, which is supposed to be an approximation to the denotation of the while loop, and I will give you back a better approximation. So this one says it unrolls the loop one time. So it says if the meaning of the expression in state s is 0, then I'm definitely going to get back s. Otherwise, if it's non-zero, then I'll take the approximate you gave me, and I'll see what c does in the state s, and I'll apply f to it. So the meaning of the while loop is the least upper bound of this chain of approximants, which turns out to be a fixed point for this operator. So we've already done some work here, right? So we need to know that the reason that this works is that there's a property inductively. The meaning of every command is actually a monotone and least upper bound preserving function on this lattice of partial functions. And that's an interesting fact about this programming language. It's a property of the language as a whole that lets us make a definition in this form. And it wouldn't be true if we added some random new kind of reflective command of the sort that you might get in Java or C# or something, where you could take a command and have a look at it and branch on how many characters it had in it or so forth. So we've already done quite, it looks trivial, but we've already done quite a lot of work by making this choice. Or if you could time things, for example, then this semantics wouldn't work. We'd have to change things. So the relationship between the different forms of semantics, again, this is all fairly undergraduate stuff. For operational and denotational, for this really simple language, they match up absolutely perfectly. So if we gave it a small step semantics, so C of S would take some number of small step transitions to skip, which is meaning we have nothing more to do, and a state S prime. This happens if and only if our obvious big step semantics says that C and S terminates in state S primed, and that happens if and only if the denotation of C in state S is defined and equal to S primed.